I'm Lishi from DDN, and today I'd like to talk about the persistent client cache. So it's a client-side cache, and we want to use that kind of cache to speed up some applications, but obviously it cannot accelerate all of the applications. There is some requirement, and we are going to talk about what kind of applications that kind of cache can speed up. So actually, this is a project collaborated by NSCC Wuxi, that is National Supercomputer Center in Wuxi of China, and the Sunway TaihuLight is running in NSCC Wuxi, and the Sunway TaihuLight is still currently the most powerful supercomputer in the world. And while the Sunway TaihuLight has a lot of cores, it has 10 million cores in the system in total. And at the time that NSCC Wuxi and DDN sit together and look at the architecture of the Sunway TaihuLight, we look at the architecture and we are trying to think of a solution to improve the I/O performance. So as you can see from this architecture, they use Lustre or other file system as the backend storage, and between the storage and the computer nodes, there is a level of I/O forwarding nodes. And at that time, we think that maybe it is a good idea to add a cache level in the I/O forwarding nodes. So that's why we have the idea of add a cache level on the Lustre client. And there are obviously a lot of benefit if we add SSD cache on Lustre client. The first benefit would be it will has much less overhead for the applications because it has no network latency, it has no LDLM latency or other kinds of Lustre latency. And it is much easier to optimize than the server-side cache because our I/O stack is simpler and there is no interference from other clients. And DDN has tried a lot of ways to implement cache on different levels, for example, on the Lustre server, but we figured out that it is much simpler to implement client-side cache because if you want to support write cache on the server side, then you need to make sure that a lot of things are ready. For example, you need to make sure that the data will be still visible when the failover happens, and you need to make sure that there will be no consistency problem when one of the cache or the OST has corruption. But if you have some client-side cache, then the requirement will be much less. And of course, if we have a cache on Lustre client, we think that the hardware requirement will be much less because you can actually use any kind of SSD or NVMe or even hard drive to speed up the application. And of course, since you have a cache level on the client, then you actually buffer some of the I/Os on the client side, and the I/Os will be regularized, and the I/O you submit to Lustre will be big and it will be sequential. And also, if the cache on the client has a lot of temporary files, then you don't need to flush the data into Lustre because those files will be removed eventually. So this is the design of PCC. It is different from other kind of cache because it provides a group of local cache. So basically, you will not have a global namespace. Each client will use the SSD or NVMe as the local cache, and we will need to format a local file system on that SSD or local device. And if you do the cached I/O, then the I/O will be directly written into the local file system, and Lustre is not involved in this I/O. And for different applications, we implement two modes. The first mode is the read-write mode. So by using the read-write mode, you can keep read-write cache on local SSD or NVMe, but you can only do that on a single client. And the other mode is read-only mode. So in the read-only mode, you can have multiple replicas on different clients, but you cannot write to that data anymore, right? Because there will be a consistency problem if you write any data into one of the clients. And this is the architecture of PCC. As you can see, we can attach SSDs to each client, and if you write as a normal I/O, then the I/O will be direct to the OSC and then go to the OST storage as usual. But if you want to cache your I/O, then the I/O can be directed to the SSD, and of course you will need a mechanism to synchronize the data from the SSD or NVMe to the Lustre storage. And at the same time, you will need a tool to fetch the data from Lustre to the local cache, and you can have a lot of local cache on multiple clients, right? And as you can see, there are a lot of work to do for the data management in the clients for the PCC. So you might need a policy engine to do that job automatically for you. So this is the architecture of the PCC. So I'm going to go into some design of the PCC. So for read-write PCC, we use HSM mechanism for data synchronization. So in each PCC client, you will need to run a HSM copy tool on each PCC client, and if there is any access from the remote client, then you will need to use that copy tool to copy the data from the local SSD or NVMe to the Lustre storage. And after the copying of the data, you will the remote client will be access that data. As you can see, if a client goes offline, then there will be some problem to access that data, because that client might be reboot, or it crashed because of some problem, or it unmount the client temporarily. So during that process, the remote client will not be able to access that data anymore. But that's fine, because it's local cache. The cache is still consistent, saved in the SSD or NVMe. And as soon as you restart that client and restart the copy tool, the data will be available for the other clients too. And also, we designed a policy to determine whether you want to put a newly created file in PCC or not. You can define several rules to match the files. For example, you can define a rule based on project ID or based on UID, GID, or the combination of those attributes. And so whenever you create a file, the policy will determine whether to cache that file or not automatically. And I'm going to introduce in several situations what will happen for the read-write PCC. So if a file is being created on read-write PCC, then a normal file will be created on the Lustre file system as usual. But at the same time, what's different is that an empty mirror of the file will be created on the local cache, and as we have said, we will need to use HSM mechanism. So so the PCC will set the HSM status to archived and released, and the archive number will be set to a proper value. That is a unique value for each client. And the second situation is when the file is being fetched to read-write PCC, then similar things will be done. First, you will need to the PCC will copy a mirror file to the local cache, and the HSM status will be set to archive and released, and the archive number will be set to the proper value. And the third situation is if a file is being accessed from the read-write PCC, as you can imagine that the data will be got from the local cache, but the metadata will still be got from Lustre. But we improved that a little bit because, as you can see, we can cache the metadata on the local cache too. So if you do the state, the client can just read the metadata directly from the local cache. So it will speed up the metadata access, right? And this is a design of read-only PCC. Read-only PCC shares almost the same framework with read-write PCC, but it is slightly different because it do not need to use HSM mechanism. It uses instead LDLM lock. The reason why read-only PCC needs to use LDLM lock because it needs to prevent other client to modify the file when you are caching a file on the read-only PCC. So currently we use group lock to do that kind of job, but as you can see, if your client is holding a group lock of the file, then other client cannot read or write to the file or from the file. So that comes a problem because normally the file should be able to be read from another client, even it is cached on PCC, right? So that's why we improve a little bit. We add a new LDLM lock mode. We call it PCC RO mode, and by using this mode, other client cannot modify this file, but it can read from that file. So again, no data can be written to the read-only PCC if the file is being cached on the read-only PCC, and we can have multiple replicas on different clients. And so if the file is being fetched to read-only PCC, then the file will be copied into the local cache, and the group lock or PCC RO lock will be grabbed by that client. And if you read from the read-only PCC, then the data will be read from the local cache, and that could be that is true for the metadata because in the current implementation, the metadata will be saved into the local cache, and it will be read from the local cache later. So we have an interface for the PCC. Actually, you can, during the runtime, you can add PCC storage to the client as you want. You can use this command to add the PCC storage. And of course, you can delete that storage if you don't want to use that anymore. And you can list how many PCC storage you have on this client. You can add as many PCC storage as you want, right? And you can fetch a file to the read-write PCC by using the LFS PCC fetch command. And if you add some options, you can add it by using read-only mode rather than read-write mode. And if you don't want that file to be cached in the PCC anymore, you can use the PCC detach command to do that. And you can check the PCC state of each Lustre file. So as you can see, there are a lot of management tasks for PCC because the PCC storage is limited. You need to sometimes to fetch data into the PCC. Sometimes you need to evict data from the PCC to get some free space for the other files. So there are some situations that you might want to fetch a file into the PCC. For example, if you detect that an application has a very suitable I/O patterns which could be accelerated by the PCC, then you can do the fetch. And if you find that a file has very high access heat, then you can fetch that file to PCC2. So actually, we implement the file heat. We implement the file heat feature for this purpose. So file heat is basically a new attribute which you can use to check how frequently the file is being accessed in the past few seconds or few hours. And you can integrate the PCC with the job scheduler too. For example, if the job scheduler knows that a job will be started in the following hours, maybe it can following minutes, maybe it can fetch the data of the job into the PCC cache, right? And you can also, as we have said, you can also use the PCC fetch to do that by yourself. The application can call the API by themselves. And by contrast, there are some conditions you might want to shrink a file from the cache. For example, if the cache is becoming full, you will need to move that file from the PCC to the storage. And if the access frequency is low or the file heat is low, then you will need to move the data from the PCC to the last OSD. So actually, we might need to implement a policy engine to do that work, because actually it is a lot of work to manage the PCC on a lot of clients. So as we have said, PCC is not able to accelerate all of the I/O patterns. So what kind of I/Os can PCC accelerate? So for the read-write PCC, the limitation is that you can only cache the file on a single client. That means the file cannot be accessed, should not be accessed by multiple clients. If the file is being accessed by multiple clients, then it is not proper to put that data into PCC, right? But at the same time, there will be no consistency if you try to do that. The performance will be bad, but there will be no problem caused by that. And for read-only PCC, as you can see, there is no write permit for the file being cached on the read-only PCC. So the write operation will get failure currently, and well, if the application will only read a subset of files, then you can fetch those files into read-only PCC, and maybe you can keep multiple replicas to speed up the performance, and also the state performance of those files can be accelerated because the metadata can be read from the SSD or NVMe directly, and it is more likely that random and the small I/O can be accelerated a lot, because at this situation, the reader ahead doesn't help much in this situation. And by using PCC, you will have much less latency. So But if you have application and you want to know whether that application is suitable to cache on PCC or not, then you will need a way to analyze the I/O patterns of the applications. That's why we think of you implement I/O pattern detector based on the changelog. So lately, Sebastian from DDN has implemented the last audit feature. So in this feature, he adds some extension to the changelog. So currently, you can add client or NID into the record of the changelog, and you can record the open and close event in the changelog. So we can use that changelog for the I/O pattern detector for the PCC purpose. For example, if you analyze the changelog and find that there is a file that only opened on a single client and the other client never touched that file, then you can cache that file onto the read-write PCC. And at the same time, if a file is only opened by multiple clients, but it is only opened using read-only mode, then you can. It's likely that it is proper to move that data into the read-only cache. So obviously, there are some limitations if you really want to use PCC, because as we know, the NVMe or SSD on the last client is limited. So the capacity limitation is one of the limitation. So the size of the cached file is limited, and the total cached data on a single client is limited. And at the same time, a file cannot be partly cached. The file can either be fully cached on the client, or there is no cache of that file. So this is a limitation of HSM mechanism, but that might change if the HSM support partial archive or restore. And another limitation because of HSM is that HSM only has 32 unique archive ID, and that means you can only have 32 read-write PCC clients currently, but we have some developers working on this situation, so maybe this problem will be solved in the near future. So this is a benchmark we run on a very simple configuration. So as you can see, we run sequential read and write on different levels of the system. The orange one is the Lustre performance, and the green one is the OSD, LDiscFS performance. Basically, we mount the OSD using LDiscFS, and we run the same benchmark on the LDiscFS, and we did the same for the PCC and the storage that PCC use. As you can see, the network is not good because the OSD LDiscFS has higher performance than the Lustre client, and as we test the EST4 file system on the PCC storage, we can see that the last client using PCC has similar performance like the EST4 file system on the PCC storage. So I think it is safe to say that the overhead of PCC is not huge. It's minimum overhead, and we can have the same conclusion for the read and write for read-write PCC. So this is a test for read-only PCC. So we instead of running a sequential I/O, we run random I/O with different I/O size. And as you can see, when the I/O size decrease, the performance decrease a lot. And we compare the read-only PCC and the Lustre performance running the same benchmark, and we find the read-only PCC has higher performance than last year, and we only use one. So the data shown here is only one PCC client, and if you have multiple clients, then you can double the performance and triple the performance, and the performance will be able to scale when you add more replica of the files. But the performance of last year, well, it is not easy to scale because there are much more limitations in last year. I didn't show it here, but I test with 2 clients. I got the double the performance. So as a quick summary, we designed and implemented the Lustre Persistent Client Cache for Sunway TaihuLight, and we think that is suitable for the architecture of Sunway TaihuLight. And we do some small benchmark, and the benchmark shows that PCC is able to accelerate some of the IOs. And we want to do the large-scale benchmark in the near future. And all of those patches have been submitted to the community. So if you want to try that and you have some NVMe or SSD environment, you can just download those patches and run that for test. And we are trying our best to try to make that happen, that these patches can be merged to 2.13. And that's all. Thank you. Any question?
Back on slide 17, did you run a test just with the local ext4 file system to see what that workload looked like against only the ext4 when you're not using PCC?
I run a similar test on the local disk, yes, using ext4. So the performance is similar with the performance shown here.
So then PCC is essentially giving you almost the local disk performance.
So, yes. It makes sense because I don't think there is any overhead or bottleneck introduced by the PCC. So essentially it is right into the local file system.